Hi everybody, I am Anthony Santosh, Assistant Professor of Chemistry in St. Joseph College of Arts and Science. I am handling physical chemistry. Let us discuss one topic in physical chemistry. Now we are going to discuss about ideal solution and Raoult's law. What is a solution? A solution is made up of two constituents at least. One is a solvent and another one is solute. We know what is a solvent. A solvent usually which dissolves the material, and the solute is which gets dissolved, and most probably solvent is present in major amount, major proportion. Solute is present in minor amount. So a solute and a solvent constitutes to make up a solution, and when it can be an ideal solution, that we will discuss now. We may know about the famous ideal gas equation. Ideal gas equation is derived from gaseous laws, Boyle's, Charles and Avogadro's laws, and a gas or a gaseous mixture which obeys ideal gas equation is named as ideal gas. Ideal means perfect. If the gaseous molecules are not obeying ideal gas equation, then that is known as non-ideal or real gases. But why we cannot use the same ideal gas equation in the case of solution? Because gaseous molecules are differing in properties when we compare it with liquid molecules. Gaseous molecules are compressible. Gaseous molecules in different conditions, they are having attractive forces, and in some cases they don't have attractive forces. But in the case of liquid, it is different. We cannot compress. They always connect to each other, and in some cases they are having more attractive forces, so they behave with viscosity, more viscosity. Okay, likewise we may have different properties. Now we are coming to the point. For finding a solution is whether it is ideal or not, we should know Raoult's law first, and then we can get the definition for ideal gas equation. Okay, let us know what is Raoult's law. The partial pressure of any volatile component of a solution at any temperature is equal to the vapor pressure of the pure component multiplied by the mole fraction of that component in the solution. So this lengthy sentence can be simplified with this equation. Pa is equal to XA into Pa0 or Pa degree. The partial pressure, what is partial pressure? That is Pa, that is indicated with Pa, partial pressure of any volatile component, that is Pa. That for if we are considering a binary solution, Pa may be a solvent or a solute. The partial pressure of the constituent, okay, partial pressure of the solvent or solute, okay, and XA, which is equal to Pa is equal to XA into Pa0. That is the vapor pressure of the pure component Pa degree 0 is multiplied by the mole fraction of the component. So A, we have a subscript A here. So if we consider a binary, how many chemicals or constituents will be there. By means 2. So one may be a solvent and another one may be a solute. Okay. So we may consider A as solvent or A may be a solute. Okay. So Pa is, for instance, we are considering that as a solvent. Okay. So Pa is the partial pressure of the constituent is equal to XA, mole fraction of the constituent, that is solvent. Pa0 is the partial pressure of the solvent when it is pure, when it is not in the solution. Binary solution means it consists of two chemical, A plus B. A is the solvent or B is, and B may be the solute. So we have two chemicals present in the particular solution. But this Pa, what is the difference between Pa and Pa0? Pa is the partial pressure of this A chemical present in the solution. What is Pa0? The partial pressure of the A chemical when it is present alone, when it is pure. Likewise, Pb is the partial pressure of the chemical B. B may be the solute here. And Xb is the mole fraction of the chemical B. And Pb0 is the partial pressure of the chemical B when it is pure, not in the solution, when it is pure. Okay. So these are the values, and after adding total partial pressure can be denoted, can be equated. P is equal to total Pa plus Pb. This may be derived like this, and when we are adding to that, we should know the values, and it may be simplified to a further value. Pi is equal to Xi into Pa0. That is a derivation. Okay. Now what is Xa? Xa is the mole fraction. How can we find out mole fraction? Mole fraction is equal to Na divided by Na plus Nb. Mole fraction of A is equal to Na divided by Na plus Nb. And Xb, that is mole fraction of B, is equal to Nb divided by Na plus Nb. So what is Na and what is Nb? Na is the number of moles of the chemical A. Here we may consider that as a solvent. So number of moles of solvent present in the mixture or binary solution. Nb, what is Nb? Nb is the number of moles of B present in the mixture or the binary solution. So number of moles of A divided by Na plus Nb. So we can collectively say this Na plus Nb as total number of moles. Since the binary solution is made up of only the number of moles of A and the number of moles of B, we can get the total number of moles. So number of moles of A divided by total number of moles gives us the mole fraction value, mole fraction of A, and the number of moles of B divided by the total number of moles gives us the mole fraction value of B. Okay, clear? So these are the values. We can get the mole fraction values here. And after adding the total vapor pressure, we get the total vapor pressure Pi is equal to Xi into Pi0 for any ith chemical, that may not be A, B, C, likewise. So this is a binary solution, so there is only two chemicals are there. But if we have more constituents present in a solution, we can prepare more number of things, more number of mole fractions, Xa, Xb and Xc, like that. So the total vapor pressure P is equal to summation of Pi. That can be that can be reached like this. Okay. And now we are going to get a definition. What is ideal? A solution of two or more constituents is said to be ideal if it obeys Raoult's law. Here we get the point. A solution of two or more constituents is said to be ideal if it obeys Raoult's law at all concentrations of and at all temperatures. Obeys Raoult's law exactly at all concentrations and at all temperatures. Clear? So what are the examples? Example for ideal solutions: N-hexane and N-heptane, N-butyl chloride and N-butyl bromide, benzene and toluene. So these mixtures are obeying Raoult's law at all concentrations and at all temperature. That is, they are obeying over the entire range of concentration, and thus they are called, that is why they are called ideal solution. Okay, now we are going to, this is the definition of ideal solution. Okay, when a solution can be ideal, likewise we can say. Now we can get ideal solution definition in other words. Okay, what is that? It is explaining or defining the ideal solution can be defined with the concept of activity. Let us see that. An ideal solution is defined as one in which the activity of each component is equal to its mole fraction under all conditions of temperature, pressure and concentration. So that is, activity of each component is equal to its mole fraction. Activity is symbolized with AI. Okay, that may be equated, that may be converted into an equation, this lengthy sentence. So if Xi is the mole fraction of the chemical, Ai is the activity of the chemical, then Ai is equal to Xi. This is another definition for ideal solution. So in this case, an ideal solution is defined as the one in which the activity of each component is equal to its mole fraction. Okay, for and these are the two definitions. For non-ideal solution, the Raoult's law is expressed as Pi is equal to Ai into Pi 0. So activity into the partial vapor pressure of the ith component when it is pure. This is another added relationship. Okay, so here we used the term activity. So we should know what is activity. Activity of a substance in any given state is thus defined as the ratio of fugacity of the substance in that state to the fugacity of the same substance in the pure state. Fugacity of the substance in that state and fugacity of the same substance in its pure state. So this ratio is known as activity. So F divided by F0, we can say that the ratio of F divided by F0 can be equated to A, that is activity of the substance. Okay, this is the, but we can get an explanation about fugacity in another video. Okay, now what is activity coefficient? Since it is related to activity, we can get the meaning now itself. For an ideal gas, activity is numerically equal to its pressure, that is A is equal to P. When for an ideal gas, A is equal to P. Ideal gas, if it obeys Raoult's law, A will be equal to P. For real gases, however, the activity is only proportional to the pressure. Activity is only proportional to its pressure. So some constant value is involved in equating the activity and pressure. So A is proportional to P and A is equal to gamma into P. This symbol is pronunciated with the sound gamma, and where gamma is the activity coefficient. Here, what is coefficient? Activity coefficient gamma. So for an ideal gas, activity is equal to P, that is pressure. But for real gases, activity is only proportional to P, directly proportional. So A is equal to the constant gamma into P, and that gamma is known as the activity coefficient. Okay, now we have got an idea about ideal solution and Raoult's law, and activity and activity coefficient also. Thank you.